Jensen Huang once said, quantum computing was 15 to 30 years away from being useful. He was wrong, and he was the one who proved it. In under a year, NVIDIA went from dismissing quantum computers as a distant curiosity to building the exact technology that connects them directly to its GPUs. That reversal alone should tell you something massive is happening inside the world's data centers. And once you understand what it is, you will never look at a server room the same way again. For most of the last decade, artificial intelligence and quantum computing have lived in completely separate worlds. AI data centers are loud, hot, and built for scale. Rows upon rows of graphics processing units chew through electricity, generate enormous heat, and require rivers of coolant just to keep running. Quantum computers, on the other hand, are the opposite kind of machine. They are fragile, painstakingly isolated, and kept colder than deep space, sometimes near absolute zero, just to keep their qubits stable for a few fleeting microseconds. For years, the idea of putting these two technologies in the same building would have sounded almost absurd. One thrives on brute force and heat. The other collapses at the slightest vibration or temperature fluctuation. But that separation is now dissolving, and it is happening faster than almost anyone in the industry predicted. The clearest proof of this shift is not a rumor or a future roadmap. It is already sitting inside real buildings. In Manhattan, Digital Realty's JFK 10 facility now hosts a quantum AI data center built in partnership with Oxford Quantum Circuits, running on NVIDIA chips inside the same physical footprint as classical AI infrastructure. In Tokyo, Equinix operates a live quantum computer inside its TY11 facility, also deployed with Oxford Quantum Circuits, sitting alongside the cloud and AI workloads that make up the rest of that data center's business. These are not experimental side projects tucked away in a university basement. They are commercial data centers, run by some of the largest real estate and infrastructure companies on the planet, and they are already treating quantum hardware as a paying tenant. Industry analysts tracking the data center sector say quantum computing has now been deployed in roughly 24 data centers worldwide, and that number is only expected to climb as more providers position quantum access as the next layer of demand, following the same pattern that cloud computing and then artificial intelligence followed before it. At an AI expo in Taiwan earlier this year, engineers and executives from companies including NVIDIA and Google stood on stage and described this shift using a specific phrase, the 2028 tipping point. Their argument was simple. Quantum computing is moving out of isolated academic experiments and into hybrid architectures that are deeply integrated with high-performance computing and artificial intelligence. Instead of quantum computers operating as standalone machines that researchers dial into remotely, they are becoming embedded components inside larger systems. Systems that are increasingly built around the same GPU infrastructure powering today's AI boom. The reasoning behind this convergence comes down to a fundamental limitation of quantum hardware itself. Qubits, the basic unit of quantum information, are extraordinarily delicate. They lose their quantum state almost as soon as they are created, a process called decoherence, and they are constantly bombarded by noise and error. To make a quantum computer useful at all, engineers need extremely fast, extremely precise classical computation running alongside it, correcting errors in real time and recalibrating the hardware from one microsecond to the next. That kind of computation, ironically, is exactly what modern AI infrastructure was built to deliver. GPUs are, at their core, machines built for massive parallel processing and rapid repetitive calculation. It turns out, those same qualities make them remarkably well suited to babysitting a fragile quantum processor. This is where NVIDIA's reversal becomes the central story. Back in 2025, Jensen Huang publicly downplayed the near-term commercial value of quantum computing, comments that reportedly wiped billions of dollars off the market value of quantum computing companies in a single day. But behind the scenes, NVIDIA was already working on something that would completely undercut that skepticism. Later that same year, the company introduced NVQLink, an open system architecture designed to tightly couple GPU computing power with quantum processors, effectively building the missing bridge between the two worlds. NVIDIA has described NVQLink as a kind of universal translator, a Rosetta Stone connecting quantum and classical supercomputers into a single coherent system. The technical achievement here is genuinely impressive. NVQLink uses a real-time interconnect built on standard Ethernet networking, achieving latency under 4 microseconds and throughput of 400 gigabits per second between the GPU and the quantum processing unit. To put that in perspective, that level of speed is what allows a classical computer to keep pace with a quantum processor's error correction demands, catching and fixing mistakes before they cascade into a completely unusable result. Paired with NVIDIA's Q-Day Q software platform, developers can now write applications that treat quantum processors, GPUs, and CPUs as parts of the same unified system, rather than as separate machines that have to be coordinated by hand. The scale of adoption behind NVQLink is what really signals that this is not a niche experiment. 17 different quantum hardware builders and 5 different quantum control system builders have aligned around this single interconnect standard. 9 United States national laboratories, including Brookhaven, Fermilab, Lawrence Berkeley, Los Alamos, MIT Lincoln Laboratory, Oak Ridge, Pacific Northwest, and Sandia, have adopted NVQLink to guide their next generation of quantum research. And the list does not stop at American borders. Supercomputing centers across Asia, Europe, and the Middle East have joined in as well, including Japan's RIKEN and AIST, South Korea's KISTI, Taiwan's National Center for High Performance Computing, Singapore's National Quantum Computing Hub, and Australia's PAWSI Supercomputing Research Center. In Europe, institutions like Italy's Sinica, France's GENSI, Germany's JSC, the UK's National Quantum Computing Center, and Poland's PCSS have signed on, alongside the United Arab Emirates Technology Innovation Institute and Saudi Arabia's King Abdullah University of Science and Technology. When you have national laboratories on 3 different continents rallying around a single piece of interconnect infrastructure within months of its release, that is not hype. That is an industry making a coordinated bet on where computing is heading next. One of the clearest early results of this convergence came from Quantinuum, a quantum computing company that used NVQLink to integrate its Helios quantum processor directly with NVIDIA GPUs. Together, they demonstrated something that had never been done before at this scale: real-time decoding of a particularly demanding class of quantum error correction codes, achieving a reaction time of just 67 microseconds. That might sound like an obscure technical detail, but it matters enormously. Helios required error correction responses within 2 milliseconds to keep its quantum information stable. The GPU-powered system beat that requirement by a factor of 32, and in doing so, improved the overall error rate of the quantum processor by more than 5 times. This is the kind of result that quietly proves a much bigger point. Quantum computers are not going to become useful by getting rid of classical computing. They are going to become useful because classical computing, specifically the GPU-driven infrastructure built for artificial intelligence, gives them the support system they desperately need to function at all. It is not just superconducting quantum processors joining this movement either. Photonic quantum computing, a completely different hardware approach that uses particles of light instead of superconducting circuits, is being pulled into the same ecosystem. A company called Quandela recently validated a low-latency integration path between its photonic quantum processors and NVIDIA's infrastructure, presenting the results at a major supercomputing conference in Hamburg. Their work demonstrated a new execution model where quantum processing units, their control systems, and GPU-accelerated infrastructure operate as a single, tightly coordinated system, rather than the quantum hardware being accessed remotely from a separate facility entirely. What this tells us is that no matter which physical approach to quantum computing ultimately wins out, whether that is superconducting qubits, trapped ions, photonics, or something else entirely, the infrastructure pattern is converging on the same basic architecture. Quantum processors sitting physically close to GPU clusters, connected by ultra-low latency interconnects, working together as parts of one hybrid machine. The commercial ecosystem forming around this convergence is moving just as quickly as the technology itself. Quantinuum, the company behind the Helios processor that proved NVQLink's error correction capabilities, completed its initial public offering in the middle of 2026, raising more than $1.5 billion and reaching a market capitalization above $17 billion almost immediately after listing. IonQ, another major player in the trapped ion approach to quantum hardware, went on an aggressive acquisition spree throughout 2025 and into 2026, buying up companies like Oxford Ionics, LightSync, Qubitekk, and Vector Atomic, while also taking a majority stake in ID Quantique, a specialist in quantum-safe cryptography. These are not small, symbolic deals. IonQ's acquisition of Oxford Ionics alone was valued at over $1 billion, and the company closed out 2025 with more than $3 billion in cash and investments on its balance sheet, giving it enormous room to keep expanding aggressively. This kind of consolidation tells you that the quantum industry is no longer just a collection of independent research projects competing for grant money. It is beginning to behave like a mature technology sector, complete with public offerings, strategic acquisitions, and the same kind of competitive maneuvering you would expect to see in any fast-growing corner of the technology world. None of this growth is happening in a vacuum, and one of the biggest constraints facing the industry right now has nothing to do with physics at all. It is talent. By the end of 2025, the global quantum industry employed just over 16,000 people working directly in the field, according to workforce data compiled by industry consortiums tracking the sector, alongside more than 8,000 new job openings posted throughout the year. Employment numbers have actually exceeded earlier industry projections, but demand is still dramatically outpacing the supply of engineers who understand both quantum physics and the high-performance computing systems now required to support it. This shortage is part of why partnerships like NVQLink matter so much strategically. By building a shared, open interconnect standard rather than forcing every quantum hardware company to develop its own proprietary bridge to classical computing, NVIDIA and its partners are lowering the barrier for smaller quantum startups and national laboratories to participate, without each of them needing to independently solve the same complex integration problem from scratch. The practical applications driving all of this investment are becoming less abstract every year as well. In the banking and financial services industry, which currently represents one of the largest single end-use segments of the entire quantum computing market, firms are exploring quantum algorithms for portfolio optimization, fraud detection, and risk analysis, tasks that involve searching through an enormous number of possible outcomes to find the best one, which happens to be exactly the kind of problem quantum computers are theoretically well suited to handle. In pharmaceuticals, researchers see quantum simulation as a way to model molecular interactions with a level of precision that classical supercomputers simply cannot achieve efficiently, potentially shortening the notoriously slow and expensive process of drug discovery. There's also a security dimension that gives this entire convergence added urgency. Quantum computers, once powerful enough, are expected to be capable of breaking many of the encryption methods that currently protect global financial systems, government communications, and private data. That looming threat has pushed both governments and private companies to accelerate investment not just in building quantum computers, but in quantum-safe cryptography, designed to protect against them, adding yet another layer of motivation behind the enormous sums of money now flowing into this space. Of course, none of this comes without enormous physical challenges, and this is where the collision between these two technologies gets genuinely complicated. AI data centers today are already operating at the edge of what conventional infrastructure can handle. Rows of GPUs draw staggering amounts of power and generate so much heat that many facilities have had to shift from air cooling to liquid cooling just to keep operations stable. Quantum computers introduce an entirely different and, in some ways, far more extreme set of demands. To keep qubits stable enough to perform useful calculations, most quantum processors need to be cooled to temperatures approaching absolute zero, some systems requiring cooling down to roughly 0.02 of a degree above absolute zero, which is colder than the depths of outer space. Executives at Equinix have been candid about just how demanding this is. Maintaining a quantum computer, they have said, is even more challenging than maintaining a rack of AI processors, because the cooling requirements are so extreme and because the hardware itself is exquisitely sensitive to vibration. That sensitivity means quantum systems cannot simply be bolted into the same room as a bank of humming GPU servers. Engineers have had to learn, often through trial and error, how to physically separate cryogenic quantum equipment from neighboring workloads to prevent vibrations from destabilizing the delicate superconducting circuits inside. This tension between raw computational scale and extreme physical delicacy is forcing data center operators to rethink their entire approach to facility design. It is no longer enough to simply add more racks and more power. Operators now have to think about zoning, vibration isolation, specialized cryogenic supply chains, and entirely new categories of technical expertise that most data center staff have never had to manage before. Researchers studying the resource demands of large-scale quantum computing have raised concerns that go beyond electricity. Some quantum cooling systems rely on rare materials, including helium-3, an isotope that is already in short supply globally. As quantum computing scales up alongside an AI industry that is already straining power grids and water resources in many regions, there's a real risk that these two technologies end up competing for the same limited pool of energy, water, and specialized materials, rather than simply sharing space peacefully. This is not a minor footnote. It is one of the central engineering and policy questions that will determine how fast this convergence can actually happen in practice. And it is a problem that governments, utility companies, and data center operators are only beginning to seriously grapple with. Despite these challenges, the financial and strategic momentum behind this convergence is enormous, and it is accelerating on almost every front you can measure. According to McKinsey's 2026 Quantum Technology Monitor, the quantum computing industry crossed $1 billion in total revenue during 2025 alone, and that figure is projected to climb to as much as $4.4 billion by 2028. Investment in quantum technology startups reached $12.6 billion in 2025, more than 6 times higher than the previous year, a jump that signals investors are no longer treating quantum computing as a speculative longshot. McKinsey's broader economic analysis now estimates that quantum technology could unlock somewhere between $1.3 trillion and $2.7 trillion in economic value worldwide by 2035, a dramatic upward revision from their earlier projections. Other research firms, tracking the narrower hardware and software market, put its size at somewhere between roughly $2 billion and $3.5 billion in 2026, with most forecasts projecting growth into the tens of billions of dollars by the early to mid-2030s. The exact numbers vary depending on which firm you ask and how they define the market, but the direction is consistent across every single one of them, and that direction is sharply upward. Governments are backing this momentum with real money, not just encouraging words. In May of 2026, the United States Department of Commerce announced just over $2 billion in CHIPS Act incentives awarded to 9 quantum computing companies, including IBM, GlobalFoundries, Atom Computing, D-Wave, Dirac, Inflection, PsiQuantum, Quantinuum, and Rigetti. As part of these deals, the federal government is taking minority equity stakes in the companies themselves, a strategy aimed at building domestic quantum manufacturing capability, the same way earlier CHIPS Act funding targeted semiconductor production. This kind of direct government investment mirrors what is happening around the world. China has committed tens of billions of dollars toward quantum research as part of its broader national technology strategy. Japan has outlined a multi-billion-dollar quantum strategy of its own. The European Union's quantum flagship program continues to fund cross-border research collaboration across the continent. When you add up national laboratory partnerships, direct government funding, and a wave of private investment all pointing in the same direction at the same time, it becomes clear that quantum computing is no longer being treated as a distant scientific curiosity. It is being treated as critical infrastructure, in the same category as semiconductors, energy, and advanced telecommunications. On the hardware side, this integration is becoming remarkably tangible. NVIDIA's DGX systems, the same accelerated computing platforms originally built to train massive AI models, are now being adapted specifically for quantum workloads. The first system integrated with NVIDIA's DGX platform for quantum control is a partnership with Quantum Machines. And NVIDIA has said it expects future integration with its large-scale NVL72 systems, the same rack-scale architecture powering some of the world's biggest AI training clusters, to significantly accelerate quantum computing development going forward. Even NVIDIA's smaller desktop-class DGX Spark system is being positioned as an accessible entry point for quantum developers who want to experiment with hybrid quantum classical programming without needing access to a full supercomputing center. What this shows is that the convergence between AI and quantum infrastructure is not limited to the largest national laboratories and hyperscale data centers. It is trickling down through NVIDIA's entire product line, from the most powerful rack-scale systems down to desktop developer kits, embedding quantum readiness into the same hardware ecosystem that already dominates artificial intelligence. The hardware itself has also been advancing at a pace that even seasoned industry watchers have found surprising. IBM launched its Nighthawk processor in late 2025, a chip built on a square lattice architecture with over 100 qubits and more than 200 tunable couplers, and the company has publicly targeted verified quantum advantage sometime in 2026, with fully fault-tolerant quantum systems expected by 2029. Google, working on a completely different superconducting architecture, demonstrated a physics simulation running 13,000 times faster than one of the world's most powerful classical supercomputers, using a processor with just 65 qubits. That result stunned much of the scientific community, not because 13,000 is an unusually large number in computing, but because it validated, for one specific class of problem, that quantum hardware really can outperform even massive classical systems by orders of magnitude. Microsoft took a different path entirely, unveiling its Majorana 2 chip in the middle of 2026, built around an experimental approach called topological qubits, which are theoretically far more resistant to the errors and instability that plague other quantum architectures. Microsoft reported coherence times of roughly 20 seconds for these topological qubits, representing something like a 1,000-fold improvement over earlier generations, and if that approach continues to scale, it could dramatically reduce the error correction burden that currently makes NVQLink and similar interconnects so essential in the first place. What ties all of these hardware breakthroughs back to the story of AI data centers is a simple but often overlooked truth. None of these advances happen in isolation anymore. Every one of these companies, IBM, Google, Microsoft, and the dozens of smaller quantum hardware startups working alongside them, is building toward a future where their quantum processors do not operate as standalone curiosities accessed through a slow remote cloud connection. They are building toward a future where quantum hardware sits physically close to and is tightly synchronized with the same GPU-based AI infrastructure that companies like NVIDIA, Microsoft, Google, and Amazon have spent the last several years scaling to unprecedented size in order to train and run today's most powerful artificial intelligence models. The data centers built for the AI boom, with their massive power capacity, their high-speed networking, and their enormous computational density, are turning out to be the exact environment quantum computing needs in order to grow from a scientific tool into a practical, commercially useful technology. That is the real story behind this collision. It is not two unrelated industries randomly bumping into each other. It is one industry, artificial intelligence, building precisely the infrastructure that the other industry, quantum computing, has been missing for decades. Looking ahead, the trajectory seems remarkably clear, even if the exact timeline remains uncertain. Industry watchers now estimate there could be somewhere between 2,000 and 5,000 quantum computers operating worldwide by the year 2030, a staggering increase from where the industry stands today. Most of these machines will not be sitting alone in university physics departments. They will be embedded inside commercial data centers, connected through interconnects like NVQLink, drawing on the same power infrastructure, the same networking backbones, and increasingly, the same specialized engineering talent that keeps today's AI clusters running around the clock. Companies that once treated AI infrastructure and quantum research as separate business lines are already beginning to merge those efforts internally, recognizing that the skills needed to manage one increasingly overlap with the skills needed to manage the other. Data center operators like Equinix and Digital Realty, who spent the last several years scrambling to build enough capacity for the AI boom, are now positioning quantum computing as the next demand layer in that same growth story, much the way cloud computing gave way to artificial intelligence as the dominant driver of data center expansion. There will inevitably be setbacks along the way. Quantum hardware remains extraordinarily difficult to build and even harder to scale, and history has already shown that early over-optimism in this field, dating all the way back to the earliest quantum computing announcements decades ago, has a habit of running ahead of what the technology can actually deliver on any given timeline. Some architectures currently generating excitement may hit unexpected walls. Some companies chasing this opportunity will inevitably fail to deliver on their promises. And some of today's most confident predictions about fault tolerance and commercial advantage will almost certainly need to be revised as engineers encounter problems that are not yet visible from the outside. The physical challenges around cooling, power consumption, and rare material supply chains are not going away either, and they may ultimately determine how quickly this convergence can scale, no matter how promising the underlying technology becomes. But the direction of travel is no longer in serious doubt within the industry itself. The interconnect technology exists and is already being adopted by national laboratories on multiple continents. The commercial data centers exist and are already hosting live quantum hardware today, not in some distant hypothetical future. The government funding exists, and it is growing larger with each passing year. And the underlying economic incentive, the desire to solve computational problems that no classical computer, no matter how large or powerful, could ever solve on its own, is not going anywhere. So when you picture the future of computing, stop imagining two separate paths, one leading toward ever larger AI models, and another leading toward exotic quantum machines locked away in research labs. Picture instead a single converged infrastructure, one where GPUs and qubits sit inside the same buildings, connected by microsecond latency interconnects, each compensating for what the other cannot do alone. The GPUs handle the brute force classical computation, the error correction, and the orchestration. The quantum processors handle the specific class of problems where classical computing, no matter how advanced, simply runs out of road. That is not a distant science fiction scenario anymore. It is happening right now, inside real data centers, backed by billions of dollars in government funding and private investment, coordinated by national laboratories across 3 continents, and driven forward by the same company that, less than 2 years ago, publicly doubted whether any of this was even worth pursuing. Jensen Huang was wrong about quantum computing being decades away. And in becoming the company that proved himself wrong, NVIDIA may have just accelerated the timeline for one of the most consequential technological convergences of this generation, right inside the very data centers already reshaping the modern world. The collision has already begun, and unlike most predictions about the future of technology, this one is not waiting for permission to arrive. It is happening now, quietly, inside buildings most people will never see, and it is only going to accelerate from here.